Welcome. In this video, we're going to take a closer look at the equilibrium or ionization constant that can be calculated for acids and bases. Remember, strong acids and bases completely dissociate or fall apart in water, so there's no reactant left, but lots of product is formed. So this means the equilibrium lies far to the right for strong acids and bases, and we use just a single arrow to show it's a complete reaction. It means there will be a lot of H3O plus or H plus, or if it's a base, a lot of OH minus, free and available in the solution. So no equilibrium constant is actually calculated because you're taking for Ka or Kb, whichever you're calculating, we would take our concentration of our product over our concentration of a reactant, and technically that would be some large number over 0. So we don't bother calculating 1 since we don't know how to work with 0 in the denominator. But with a weak acid or base, only some of the hydrogen or hydroxide ions fall off or dissociate. So now the equilibrium lies far to the left, and we use the double arrow to show it's a reversible reaction. This means only a little bit of H plus or OH minus is free and available in the solution. So now we can calculate an equilibrium constant for a weak acid or a weak base, and it gives us a good idea of how much or how little it dissociates, and it allows us to compare weak acids and bases to each other. In reality, most acids and bases only partially dissociate. Most of them are a weak acid or base. So we call it the ionization constant, and we use K sub A or K sub B to represent each one. So acid or base strength and the amount of ionization really indicates equilibrium. So when you calculate KEQ, now we call it Ka or Kb in the ionization constant, but we're still looking at the concentration of products over reactants. So the bigger Ka or Kb gets, the more it dissociates. The smaller, the less it dissociates, and the weaker it is. And you can look up Ka and Kb values on a table, like table 18.4 on page 647. Or you can calculate them. But remember, we don't calculate Ka or Kb for strong acids or bases. So if we look at my examples here, you should easily be able to look at the equation and decide if they're strong or weak acids and bases. The first one, even though CH3COOH doesn't look like a typical acid, I see that it loses a hydrogen, and I see that there's a reversible arrow, so I know this is a weak acid. NaOH forms Na plus and OH minus, and it's a single arrow, so that's my hint that this is a strong base. H2SO4 also has a single arrow, and it's losing the H plus, so this is a strong base. And CH3NH2 is taking a hydrogen from water, so this is a weak base since it uses the double arrow. And finally then, we could calculate an ionization constant for the first and the last one. So for the first one, it would be a Ka value, and I would take the concentration of my products, so CH3 COO minus times the concentration of H3O plus, and I divide that by the product of CH3 COOH times the concentration of water. Water technically will always be a concentration of 1 because we just use its density. So you don't even have to include the water in there if you don't want to. And then for my weak base, my Kb value down here would be the concentration of my products times, I'm going to need more room here, so let me pause.